Okay, everyone be quiet and listen to me now. This is serious. Okay, so the stuff to remember, lab exam 3 is this week in lab. It covers everything that we've done in lab. And then on Thursday is quiz, whatever, 3. Remember that these are always cumulative. To get ready for them, go back and skim your notes, read your notes, try to pick out the key ideas, I think if you had unlimited time or, wanted to put a lot of time into it, the way probably to get ready for a quiz, the best way maybe would be to go through your notes and write an outline of the big ideas, You can also just sort of do that in your head, but I think writing outlines is always helpful. It helps you sort of frame how all the ideas in the class fit together instead of just like holding ideas, You have like this organized, you know what I mean? And then exam 3. After the lab exam this week, after your lab this week, no more labs. We're done with labs. So there's nothing next week. And then exam 3 is 1 week from Thursday. And then while we're talking about all this stuff, the last exam, the final, is really the only thing you have left besides getting in homework. Let's look at when that's scheduled. I don't know it off the top of my head. Okay, so we are a Tuesday, Thursday class. Tuesday, Thursday, we meet at noon. So our final is Thursday, the 14th of December from 11 to 1. You won't need more than 2 hours. A lot of people won't even need more than 1 hour. So that's Thursday of finals week from 11 to 1. I'm also going to put one more quiz, this same, so it'll be broken into 2 parts, a quiz and a test. Still the whole thing, I mean, I'd say maybe plan on an hour and a half or something, but I think most people will be gone in a lot less time than that. Any questions about the end of the semester? This is really all the stuff that you have left. The people who had lab today already did this, so congratulations. Okay, anybody have any homework questions or overall questions? Yeah.
Can you walk through 2B?
Yeah. Yeah, for sure. Okay, so number 2, you have this rectangular object, and it's rotating about an axis up at the top right, and it has an angular velocity of -6 radians per second and -12.5 for the angular acceleration. Okay, so let's start trying to draw this. So this is rotational kinematics number 2. This is the axis. And we're told that it's rotating. So the angular velocity is -6. Is that clockwise or counterclockwise? Clockwise, yep. So any point on here is making a circle around that axis. So this is the angular velocity. I guess I'll write the negative in there. And the angular acceleration is also clockwise at -12.5 radians per second squared. Is it speeding up or slowing down? So that just has to do with whether the signs are opposite or the same. Those signs are the same, so it's speeding up. Now we get to B. That's the one you asked about. So what's the speed of the point A? Okay, I didn't look at what A is. Okay. So the point that we're interested in is this one down here. Okay, this one's the axis. And let's first just think for a second about what this point A is doing. It's moving in a circular path around that axis. So it's following a path like this, okay? Let's think about the direction of the velocity and the tangential acceleration and the centripetal acceleration. These are things that I think you're asked to do probably. You have to, yeah. So, okay, first, the velocity. It's moving clockwise. So the velocity is going to be tangent to the path in the direction of motion. Next, let's think about the tangential acceleration. Well, the tangential acceleration is going to be in the same direction as the velocity because we know that it's speeding up. So the tangential acceleration is like this. And then the centripetal acceleration is always toward the center of the circle. So like this. It makes it a little more challenging to visualize because this point A isn't directly below the axis. But remember that every point is always moving in a circle around the axis. So you can sort of work from there. And now let's calculate the magnitudes of these. The magnitude of the velocity is the speed. That's what it asks for part B. And so the speed is equal to the magnitude of the angular velocity times the distance from that point to the axis. Okay? Well, now this is a little bit of a pain because I'm going to write this as R for now, but what's the distance from A to the axis? You have to think of that as like a right triangle and use the Pythagorean theorem. So this R is equal to what are the distances? 1.5 and 0.35. So this r is going to be the square root of 1.5 squared plus 0.35 squared. Can someone tell me what that is? 1.54 meters. And so the speed is 6 times 1.54, which is so 9.24. Is that right? 9.24 meters per second. And for the velocity vector, you could just say, I don't think it asks for that, maybe, but the velocity vector then is 9.24 meters per second in the direction of that arrow that's drawn. Coming up with the components of that vector would be a little bit of a pain if you used a usual coordinate system. But if you were super clever about it, you could say, I'm not using a usual coordinate system. I'm using a coordinate system oriented like this. And then this is just in the negative x direction. So your velocity vector would be negative 9.240 in this funny coordinate system. You can always use any orientation of coordinate system you want. That's why we chose a different one when we did things sliding and rolling on inclines, because it just made the math a little easier. But if you're ever asked for a vector, this is a perfectly good answer too, you know, just there's the magnitude, draw the direction, and that's it. Okay, what about the magnitudes of the tangential and centripetal acceleration? Well, the magnitude of the tangential acceleration is the absolute value of the angular acceleration times r. So this is 12.5 times 9.24. What do you get for that?
So not 1.54 because it's radian.
Say that again?
So not
Oh,
1.54.
yes, I'm sorry. Yeah, that times r, right. So what was that, 1.54? Yes, thank you. Okay, multiply that instead. That's better. 19.25. That's meters per second squared. And we've already figured out that that's in the same direction. So the tangential acceleration vector is 19.25 in this direction. And then the centripetal acceleration magnitude is v squared over r. So that is 9.24 squared divided by 1.54. And what do you get for that?
55.44 meters per second squared.
55.44.
Yep.
And so the centripetal acceleration vector is 55.44 meters per second squared in that direction. And so then the total acceleration is just the sum of those two parts. If you're using a funny coordinate system, this is in the negative x direction, this is in the positive y direction, So you can just add those and come up with the components, but that's not something that you'll be asked to do on tests or homework or anything like that. Any other questions on that one? Okay. Any other homework questions you'd like me to go through? Okay, well, I want you to notice, so since we just did this, notice this relationship between, so if you know the velocity and if you know the angular velocity and you know the angular acceleration, you can come up with velocity vectors and acceleration vectors. Well, that's going to be useful to us because we're about to get into rigid body kinetics, angular kinetics. And with kinetics, we're going to calculate angular accelerations based on forces and locations and stuff. So like in any case where you're given the forces and the locations, you can calculate the angular acceleration and then use that to calculate stuff about accelerations of points and stuff like that. All right, so now we're getting into rotational kinetics. And kinetics always means combining kinematics with the causes of the motion. So that's forces, masses. So now we're combining rotational kinematics with the causes of motion. One thing I want you to notice is that now that we've gone from particle motion to rigid body motion, we're talking about bodies that now we're taking into account the length dimensions of bodies. And so that means that, notice up until now, like the location where forces are applied to a body hasn't mattered at all. And the reason is we've just been treating bodies as existing at a single point. So basically everything happens at the center of mass. Now it does matter where forces are applied. A force can be applied to this side of a board or this side of a board, and it's going to have an effect on the motion, you know? So in rigid body motion, the location where a force acts matters. And the most important of these is the weight force. We're going to always treat a body's weight force we're going to always treat it as acting at its center of mass. Well, since we're just doing all shapes that are rectangles and a couple of circles, but the center of mass is just the middle of a circle, and it's just the middle of a rectangle, like the middle along the long axis and then the middle along the short axis. But you always have to remember to put the weight at the center of mass. The big equation that we're heading towards is rotational Newton's second law. I call it that because the form of it looks exactly like Newton's second law, and you derive it from Newton's second law. We're not going to derive it in this class, but that's where it comes from. And rotational Newton's second law says, add up all the moments, otherwise known as torques, about the point A, the axis, the hinge, That's equal to the moment of inertia about that hinge times the angular acceleration. So let me write this down. So this MA net is the sum of all the moments about A. Capital I sub A is the moment of inertia of the body about A. And the angular acceleration, we've already talked about what that is. So okay, Newton's second law says the forces, you add up all the forces, that's equal to the masses, the mass of the body that you're looking at, times its acceleration. This says kind of the same thing. Add up all of these moments, the things that cause rotation. That's equal to the moment of inertia, that's a body's resistance to rotation, times the angular acceleration. So it's easy to remember if you think of it as kind of a version of Newton's second law. Well, before we can use it, I have to define two things here. We already know the angular acceleration. We just have to talk about what the moment of inertia and the moment is. So I'll start with the moment of inertia. And I'm going to always denote that I sub something. And let's say about a point. So the A is the point that it's about. And the moment of inertia is a positive scalar quantity. Scalar means it's not a vector. That's large if an object is hard to rotate. And small if an object is easy to rotate. You know, think of that in comparison to the mass of an object. This is really just a rotational version of mass. The mass of an object is big if it's hard to move, small if it's easy to move. This is the same thing, but talking about rotations. A body has a high value of I sub A if mass is distributed far from the axis A and a body has a low moment of inertia if mass is pulled tightly near that point A, that axis A. So two things that have the exact same amount of mass, one can be easy to start rotating, one can be hard to start rotating. If in one of them all that mass is sucked really close to where that hinge is, And in the other one, it's spread out really far from where that hinge is. Okay. I think this is a good intuitive example. You know, like Olympic sports, Olympic type sports, acrobatic sports, give you a lot of examples of how this works intuitively. I'm going to think about someone flipping in like diving or gymnastics. So think about these two cases, a single person doing, you know, a double flip or whatever. So in one case, they position their body like this. And in the other case, they position their body like this. If you're watching gymnastics and someone is starting their routine, they might do the stretched out one for their first tumbling thing when they're fresh. And then at the end of their routine, they might do a double flip in this tucked position. It's harder to, the reason for that is it's harder to do a double flip when your body is in a stretched out position, because even though it's the same person and the same amount of mass, that mass is distributed far from, in this case, well, what's the axis? There's not really a physical axis, but for math purposes, the axis is their center of mass. And so if you're stretched out, you're getting your mass far from the center of mass. Not all of it, some's right at the center of mass, but a lot of it is stretched out far from it. That means that it's hard to get your body rotating in that position, and that means you have to have more power to get up higher. It takes longer to complete these two flips, you know? Then when you're tireder, you don't have the power to generate quite as much height. You do something like this. Since you have all of your mass sucked in close to your center of mass, you can do that rotation a lot faster, and so you don't have to get up quite as high to do that. Although double flips are still hard, I think. I don't know, maybe I'll try one.
Sure.
Just do my little round off thing like off the edge of the table. That should give me the height I need. I'm not doing that. Okay, but anyone have any questions about that idea? Most of the calculations we're going to do are just going to involve rectangles. And so I'm just going to give you formulas for rotating rectangles about certain points on the rectangle. The units for moment of inertia are always units of mass times units of length squared. And so the SI units are kilogram meters squared. So no matter what the shape of the object is, the units of the mass moment of inertia are kilogram meters squared. And here are the formulas that you're going to need. There are a couple of problems you'll do with rotations of circular shapes. But in those problems, I give you the formulas to use for those. So, okay, so here are the moments of inertia for rectangles with various hinge locations. So rotating about various places on the rectangle. Okay, so if you have a rectangle, and I'll call the long side L, and the short side W, what would you guess is the point? So where would you want the hinge to be on this rectangle to make it the easiest to start it rotating? Anyone? Center. That's the answer, yep. So let's start with, I'll call that point A. And if you're calculating the moment of inertia about that point A, the formula is 1/12 times the mass of the rectangle times the quantity length squared plus width squared. And that all comes from an integral definition using calculus. We're not going to go into where that comes from, but the next point I want to think about is, well, what if you go all the way to the end of the short side, but you're in the middle of the long side? So there are two possible places like that, here and here. Okay? So what about a hinge at either one of these? I'll call that B. You can imagine that putting a hinge at either of those two locations, B, wouldn't affect how hard it is to get this thing rotating, right? So it makes sense that those formulas would be the same because of sort of symmetry, right? Well, the formula for B is 1/12 times the mass times the length squared plus 1/3 times the mass times the width squared. If I multiplied the 1/12 m through this parentheses, I would get 1/12 m L squared plus 1/12 m W squared. So the only thing that changes is on the side that we're at the end of, we're at the end of the W side. We're multiplying by, it's 4 times as big of a contribution to this mass moment of inertia, 1/3 instead of 1/12. Then the next points we'll consider are, how about if you're at the center of the W side, but all the way at the end of the L side? So that would be C there or there. And the formula for the moment of inertia, if the hinge is at C, is 1/3 mL squared plus 1/12 mW squared. So whichever one of these sides you're at the end of, that's the term that you multiply by 1/3 instead of 1/12 if you're trying to make sense out of this. If you don't want to make sense out of it, that's fine. I'm going to give you these formulas. Okay? And then the last ones we'll use will be at the corners. And all 4 of these use the same formula. So D, 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 D. Anybody want to guess what this formula is going to be? What?
1/3.
Yeah, exactly. Perfect. 1/3 times m times the quantity L squared plus W squared. So these moments of inertia get smaller as you go this way. larger as you go this way. Okay. One thing I want you to notice is in all of these expressions, the length and the width are both squared, which means differences in the lengths of the two dimensions get amplified by that squaring, you know? So the effect of that is that because of the squares, because we're squaring these terms, you can often just treat the smaller dimension as 0 without affecting the answer very much. You know, without adding much error. So if you ever see a problem that only gives the long dimension of a rectangle, and it doesn't even give a number for the small dimension, just treat it as 0. Let me show you how that works. So let's say that we have a length of, I'm going to use one that's going to come up later. Okay, so let's say that the length is 2 meters. And the width is 0.1 meters. And let's calculate the moment of inertia around the center. Okay. Well, to get the true answer, you'd go 1/12 times the mass. Let's give it a mass of, let's say the mass is, I think 10 kilograms is what I'm going to use later. Okay, so 1/12 times 10 times 2 squared plus 0.1 squared. So that is 0.83 repeating times, in the parentheses, 2 squared is 4, 0.1 squared is 0.01, so 4.01. And you get something like point. What do you get for that? What am I doing weird? 12 times 10. That seems right. Oh, yeah. Okay. Can someone multiply that for me?
3.328.
3.3 what?
28.
28. Okay, and then let's do it, you know, how close is it if you treat the small side as 0? then you get IA is equal to 1/12 times 10 times 2 squared plus 0 squared. And so you get 3 point, well, this must have like round off in it. But this is 3.3 repeating, I think. Let me just get an exact value for this. I think it's going to be something like 3.34 if you keep enough digits. But you can see, you know, the difference is pretty tiny there. Never mind. Well, like, why is that difference so tiny? The difference between 2 meters and 0.1 meters is 20, a factor of 20, right? And so when you square them, you end up with a difference of 20 squared for a factor. So the contribution of this one is 400 times as big as the contribution of this one. And that's why a lot of times you can just throw away the small dimension without really any problems. Yeah.
Does that only work if it's like under 1?
No, it works. It always works, but I would say probably about a factor of 10 is about the smallest where you would want to use that approximation. But if they're different by a factor of 10, then when you square them, they're different by a factor of 100. So you'll be off by 1% if they're 10 times different, you know. If it's, you know, if one is only twice as long as the other one, then the contributions will be a factor of 4, which probably isn't enough to just throw out that term and still feel good about your answers, you know. Okay, so now let's talk about moments. Moment, or you can also call it a torque. About a point. Physicists tend to use the words moment and torque interchangeably. They mean the exact same thing. Engineers, a torque for an engineer means a very specific combination of moments, and so they don't tend to use it interchangeably. But this is physics, so let's call those the same thing. So let's say that you have this object. Doesn't matter what the object looks like. And let's say that you have a hinge here. A is the hinge. And at this point P, let's say we have a force. Let me try that again. F that happens to be perpendicular to the line between these 2 points. Okay? And let's call the distance between the hinge and where that force is applied D. So if the force F is perpendicular to the line from A to P, so notice that doesn't always excuse me. There's no reason that always has to be the case. I could have applied that force F at P off to the left and then it just wouldn't be perpendicular to that line, and there's nothing you can do about it, okay? But if it happens to be perpendicular to that line, then the moment is plus or minus the force times that distance d. And to come up with the sign, positive is if that force would cause a counterclockwise rotation, and negative is if it would cause a clockwise rotation. So counterclockwise is positive, just like we had before. And clockwise is negative. So in this case, the way I've drawn this, with that force F, and ignore everything else, like you're not thinking about whether there's friction, you're not thinking about whether this is on the ground or whether there are any other forces acting. You're just thinking, if this thing is in space, connected to a hinge at this point, I don't know what that hinge is doing in space, but, and you apply that force F, would this body rotate clockwise or counterclockwise?
Clockwise.
Clockwise, right. So in this case, it would be negative. Before I do an example, let me give you sort of an intuitive idea of what this intuitive idea. So a moment or a torque is a thing that causes a rotation. So let's think of a bolt that you're trying to turn with a wrench. And let's say you know that you're capable of applying 100 newtons of force to this wrench. Do you want to apply it here? Or here? Or here? You know from experience that if this bolt is, you're having trouble turning this bolt, you want to apply as much force as you can, as far away from the bolt as you can. That's why they make giant monkey wrenches too. If you have to turn really tight things, then you need an extra long. And you can see how that works with this formula. So even though these are all 100 Newton forces, what would be the distance d for this one? 0. It's acting right on the bolt. And you know that, hopefully, you've figured out by this point in your lives that if you try to turn a bolt by just pressing straight down on the head of the, straight down on the bolt, you could apply 1 billion newtons of force and it would never turn. It would just rip the bolt in half, That's because that d is 0. If it's not too badly stuck, you could apply that 100 Newton force at the middle, and you'd have a d value that's half the length of that wrench. And so it would tend to turn it. But the best results you would get is if you make that value of d as big as possible. Notice that the line from the axis, the hinge, to where the force is applied is perpendicular to that force. So you can use that. Okay? Okay, so let's say that we have a rectangle. Let's say that the hinge is over here. This length is 1 meter. This length is 0.25 meters. And let's say that we apply a force to this point upwards of 30 newtons. Okay, so the question is, what's the moment produced by that 30 Newton force? Well, first we have to make sure that that force is perpendicular to the line between the hinge and where the force is applied. Is it in this case? Can you visualize that? You can always just draw out a line to help you see it. But yeah, so these two are perpendicular. So the formula we have works. And so the moment is equal to plus or minus a force of 30 times what's the length of that dotted line I drew? That's the D. 1, yep. And would that force make it rotate clockwise or counterclockwise? Clockwise, so it's negative. So our moment is equal to negative 30. Oh, I didn't give you the units yet, but you can see from the formula that you're just multiplying. Where'd it go? You're just multiplying units of force to units of length. So this is Newton meters. Okay, so units for a moment are units of force times units of length. And that means that the SI units are always Newton meters. One thing that's interesting about this is, remember, newtons are already something else. Newtons are already kilogram meters per second squared. And so if you multiply another meter to it, you get kilograms meters squared per second squared, which happens to be our definition of joules. So the units for a moment are really joules, but we're not going to use it that because I think it helps you keep straight whether you're thinking about energy or whether you're thinking about moments. Even though they have the same units, they're not the same thing. Okay, so don't call it joules, even though it is. Okay, here's the last thing about calculating moments. So I said if you happen to get, really infinitely lucky, like probability-wise, what are the chances that your force is perpendicular to your to the line between the about point and where the force is applied? The chance really is 0, you know. So what do you do if they're not perpendicular to each other? So what if the force and, that line D are not perpendicular? Well, it turns out that you can always move any force along what's called its line of action without changing the problem. So I'll show you a picture of what that is. So you can always move a force along its line of action until they are perpendicular. Okay, so for example, if you have a body like this and your force is applied here and your hinge is over here, if you draw the line between those 2 points, you can see that those aren't perpendicular. But the line of action of the force, you can think of that as like the infinitely long line that that force vector lives in. So that's the line of action. And you can just think about sliding that force along the line of action until they are perpendicular. So let's say that we slide the force over to about here. Notice it's not even on the body. That's fine. It's just a mathematical thing that lets you do this calculation. And now the line from A to where the force is applied is perpendicular to the force. And now we can do that calculation. So this then is our D. Anybody have any questions about that? Let's just do a problem or two where you can see how you use that. Okay, so let's say we have a rectangle with a height of 3 meters. And a width of 1 meter. And let's say that we have a 20 Newton force this way. And a 10 Newton force this way. And let's think of 2 different hinges. First, we'll do the one at A. And second, we'll do the one at B. So the question is, what's the net, the total moment about? So first we'll do it about A, and then second we'll do it about B. And we're going to get different answers for those 2 different cases. All right, so for part A, the line of action of the 10 Newton force is this. And the line of action of the 20 Newton force is this. So we can move those forces anywhere we want along those lines, and we're just trying to choose the points where the line between the points is perpendicular to the force. So I'm going to move the 10 Newton force to here. And I'm going to move the 20 Newton force to here. Are you with me on that? Okay, so MA for the 20 Newton force is plus or minus, the force is 20. What's the distance D? $1.5. Anybody have any questions about that? Do you see that? And would that 20 Newton force make this body rotate clockwise or counterclockwise around A? Clockwise, yep. If you gave this a bump here, tap it, it will go this way. Anybody have any questions about that? Want me to clarify that a little more? So this is clockwise, and so we get negative 30 Newton meters. Now we'll do the same thing for the 10 Newton force. Plus or minus, the force is 10. What's D for the 10 Newton force? 0.5. Yep. Would that make it rotate clockwise or counterclockwise around A? Clockwise, these are all going to be clockwise, that's boring, but so you get negative 5 Newton meters. And so the net moment is negative 35 Newton meters. Any questions about that? Okay, now let's do the same thing, but we're going to assume the hinge is at B now. So for the 20, so now the 20, that 20 Newton force is actually already perpendicular to the line between B and where the force is applied. So you don't have to imagine moving that at all. What's the distance for the 20 Newton force? 3, yep. So you have 20, 3. This is clockwise again, so negative 60 Newton meters. Then the moment about B for the 10, that's plus or minus 10. This one actually we don't have to move along its line of action either. What's the distance for the 10 Newton? 1. And that's clockwise again. So this is negative 10 Newton meters. And so the net moment is negative 70 Newton meters, which you can see is not the same as what we had before. Moving that hinge affects what that value is going to be. Okay, well, let me do, now we finally can start doing rotational Newton's second law problems. So let's say that we have a hinge attached to a wall. And a 2-meter long beam. And I'm going to ignore the thickness. We're going to assume that that's just small compared to the 2 meters. And let's say that the mass of this beam is 10 kilograms. What's the angular acceleration of this beam? Well, I'm going to start by calculating the mass moment of inertia, the moment of inertia of that beam, just using the formula. And then we're going to calculate the moments of the forces. One thing that you always have to do in rotational Newton's second law problems is you have to recognize that there are forces applied to the body by the hinge itself. But since what's the distance from the hinge to the hinge, basically? It's 0. And so even though there are forces there that need to be in your free body diagram, an X and a Y force, they're not going to show up in rotational Newton's second law. They would show up if you did Newton's second law, and we'll get some practice with that in the next couple days. But okay, so the first thing I'm going to do is calculate the moment of inertia. That is 1/3 times the mass times the length squared, plus we're assuming that the thickness is 0, so this part is 0. And we get a value of 13.3 repeating kilogram meters squared. And now I'll draw a free body diagram. At the hinge, we have two unknown forces. I'll call them Rx in the X direction and Ry in the Y direction. Those aren't going to come into these calculations, but you need to remember to put them in the free body diagram. And then the weight acts right at the center of the board. So right at the middle, we have 10 times 9.81, so a force of 98.1 newtons. The moment produced by those forces are, like I said, are 0. That's how it's always going to be. That's because D is equal to 0. For the weight force, so I'll call that MA for the weight. That's plus or minus the force of 98.1 times what's the perpendicular distance from that weight force to the hinge. The whole thing was 2 meters, so that's 1 meter, half of the length. And does that weight force make this rotate clockwise or counterclockwise around that hinge? Clockwise again. And so MA net, if you add them all up, is negative 98.1. And now rotational Newton's second law says negative 98.1 is equal to 13.3 repeating times alpha. Divide both sides by 13.3 repeating, and you get something like alpha is equal to negative 7.35 radians per second squared. So since angular acceleration is negative, that says that this thing is going to rotate this way, which makes sense. I mean, that's what you would expect gravity to do to that. And if I had, now using rotational Newton's second law, there's no way to calculate angular velocity. But if I had told you what the angular velocity is before we started, then we could go and calculate velocity vectors. We could use this angular acceleration to calculate the tangential acceleration of a point. We could use the angular velocity to calculate the centripetal acceleration of the point, and we could calculate acceleration vectors at individual points on this body. And we'll do that a little bit too in the next couple days. Anybody have any last questions before? So the homework that I'm going to give you to work on is just a small number of problems, just calculating net moments, getting used to moving forces along their line of action, stuff like that. Okay, that's all.